So what happens now when we have something, I mean, when this is a case, we have compression here, then after that is all tension. You can see that now. Okay. And we know that this is our stress X is equal to 0 line. Okay. So IE now over here, when it crosses 0, this is our position of neutral axis. Okay. That is the position of neutral axis. Okay. So what I want to highlight down here, over here, okay, on this line over here, which I'm going to highlight in yellow now, this is actually also, right, the position of the geometric centroid. Okay. So what I've shown you down here is if or when, not if, okay, this is true, when it is under eccentric loading, there will be a what? A shift. Okay. There will be a shift of the what? Neutral axis, right? Because before that, what we see is the neutral axis and the centroid position are the same. Under this situation, there's a shift of the neutral axis away from the geometric centroid. Okay, so that's why a lot of times textbook even make the same mistake. They assume that the geometric, they'll say the neutral axis determine the neutral axis, determine the new. No. Determine the geometric centroid, because we have shown you at this stage the geometric centroid and the neutral axis are not at the same point, because the geometric centroid is determined by the cross-sectional profile of the structure, whereas the neutral axis occur when stress, normal stress X is equal to 0. Okay, so just to quickly summarize what we have I have just or what you have just observed is this, which is important. So in eccentric, okay, symmetrical bending, the position of the geometric centroid and neutral axis are not the same. Okay, so the if it is centric symmetrical, okay, the geometric centroid and neutral axis are the same. Under eccentric symmetrical bending, the position of the geometric and neutral axis are not the same. Okay, that is what I like to highlight. As I said, a lot of time, it is a very common mistake to make, that when you find I'm going to use geometry to find a neutral axis. No, you can't do that. Okay, I just show you why. Right. Next we are going to deal with this example over here. Okay, this example is not difficult, but it's the first time you're seeing it. Okay, so it can deem a bit challenging initially, but it's not. Right. So this is a example. Again, it's not so straightforward when you just look at it. Okay. So what we have is we have a cantilever beam AB has a rectangular cross section of 100 by 200 millimeter. It declared that knowing that the tension in the cable, they declare that the cable is in tension. And remember, we've gone through buckling, right? And I mentioned to you all, the rope, if a rope is in compression, it's not taking any load at all, right? If you put a string and you put in compression, okay, you put a string in one end of your finger and the other one on your right hand of your finger, you push two fingers together, there's no resistance, right? So the rope has no resistance under compression load. But when you pull, there's resistance. At one stage, when you hit the length of the with your fingers are at the length of the rope, you cannot pull anymore, or you cannot you find resistance in pulling. So this shows that rope can carry only tensile load. Okay. So they declare that BD is 10.4 kilogram, and neglect of the weight of the beam we are just going to determine the normal stresses. Okay. We are not at this stage, we are not going to determine the load in the compression. I mean in shearing. I'm not taught shearing yet. Okay. So the first thing that we are going to do, okay, is we are going to draw a multi body free body diagram. Okay. So we are going to look at the beam first. Okay. So we're going to or declare our transformation. Okay. So this is our X. This is our Y. We have a rotation at a Z. Okay. So we have a rotation over there. And then we are going to sketch our multi-body free body diagram. Okay. So we have a beam. I realize that I have to do this because in the term test, I realized the multi-body free body diagram, you did not do a very good job of it. Okay. So I'm going to do the multi-body free body diagram over here. All right. So we also know that BD, okay, so BD is at a certain angle. This is our BD line. And our BD line, so we are given BD, right? So this is our point D. This is our point B, right? And over here, we were told that this is under tensile, 10.4 kilonewton. So when it's tensile, you draw the rope going in tension. Okay. However, when you do this, and exactly at point B, right? Exactly at point B, what will happen is when you apply Newton's third law, action equal to reaction, same in magnitude, different in what direction? So this in turn you will have two forces. It's a vector. Okay. So over here you have by, and over here you have a bx. Right? You have a by and you have a what? You have a bx. Now at point E, they declare that we have a load coming down, right? And this load happened to be 14 times 10 to the power 3 Newton. Okay, there's. And then on the side of the beam over here at point A, right? We observe that we know that there is a load coming in this way, right? And this is going to be our AX. Now, Y is coming in this way, right? Because it has to push in, you have to oppose Bx. If not, the structure will not be under static equilibrium. Okay. And then we are also aware, right? We are also aware that there is a moment, right? So there's a moment at point A. So the moment at point A, we have not calculated. In fact, we can see what is the moment of point A by doing some simple calculation. Okay, so we have I'm going to write down here, we have a moment at point A, right? Because it is what? It is built in down here. Okay, it is built. So we have a moment. So whether the moment will come down this way or will go up this way, okay, we don't know yet. I repeat, we don't know yet. Okay, okay, don't know yet. Okay, don't know yet. Okay. Now, if we were to look at point D, right, we know that we have a force coming down this way, right? And we are also aware for the force to go down this way, we need to have a dy, dx, and over here we need to have our dy, right? Because the rope is under tension, and we are applying Newton's third law. Okay, right? So here we go. Okay, so the first thing we do is we want to find what is bx and what is by. Okay, so we are given that fbd. So what is fbd? So we are given fbd over here. So fbd will be equal to what? Fbd will be equal to 10.4 times 10 to the power 3 Newton. Okay, so now we want to find by. Okay, we want to find by and bx. Okay, now if we look at distance wise, if we look at can I do it based on geometry? Did they give us the length of bd? Let me see. They did not give us the length for bd. Okay, so hold on. Yeah, they did not. So we have to find this angle now. Okay, and this angle is going to be theta, right? So the angle theta is based from here to here. Okay. So we know that tangent theta is equal to 0.9 plus another 0.9. Okay. So it is equal to 0.75 divided by 1.8. So from here, theta, okay, 0.75 divided by 0.9 plus 0.6, 0.9 plus 1.8. 0.75 divided by 1.8 inverse tangent is equal to 22.6 degrees. Okay, so what we have is 22.62 degrees. All right. So from here, we can quickly or easily write out that over here, this angle over here is our 22.62. So by is equal to 10.4 times over 10 to the power 3, and then sine of 22.62. Okay, so 10.4 times by sine 22.62, 10.4 to 3 times by 22.6 sine 22.62. I get 4 times 10 to the power 3 Newton. And then likewise, we can do our Bx is equal to 10.4 times 10 to the power 3 cos 22.62. Okay. So this is equal to 9.6. Okay. So we know one is at By is at 4 kilonewton and Bx is at 9.6, right? So now if we're going to take moment at let's say I'm going to do something further. Okay, we are going to find the moment at point A. Okay, we're going to point moment at point A, right? So what I'm going to do is I'm going to do dimension of moment, right? In the z-axis at point A, the whole thing is equal to 0. Okay. So I'm going to assume now, okay, I'm going to assume now that the moment is going to go anti-clockwise. Okay, I'm going to assume this one. Okay.